Good morning, students. Yesterday, or rather last lesson, uh, we have practically designed and implemented a common emitter small signal amplifier. And as I promised yesterday, that today's lesson we shall analyze the performance characteristics or performance parameters of that amplifier. In the meantime, I want to go back to come to this calculation also. I shall zoom in a little bit. Here, found the value of 6 kilo ohm in our last class. And then I told that you take R2 as 2.2 kilo ohm and then calculate R1. And there is another method. And to me, it appeared that it's a better method. So I thought I should give that to you also. Since RB is 6 kilo ohm, RB is R1 R2 in parallel, that is equal to 6. That is equation 3. Also, the value of VBB we have found earlier. Value of VBB we have found earlier to be value of VBB we found earlier, and we repeat it once again. Value of VBB was found 1.76 volt, because VBB will be equal to RB multiplied by IBQ current plus this resistor drop across this resistor beta RE IBQ plus this barrier voltage. If you do this calculation, it is 1.67 volt. If VBB is 1.67 volt, then in terms of the potential divider, VBB is equal to VCC R2 divided by R1 per R2 is equal to this 1.67. This is equation 3, this is equation 4. In both equations, there are two variables, R1 and R2. If you just solve them by linear equation, you will find R1 is equal to 34K and R2 is equal to 73K, 7.3K. We shall take these values actually, but in our last lesson's value also was same, so was okay so far as the quiescent point is concerned, because the ratio is same, right? So this is R1 34 and R2 7.3. Accordingly, we change this table. R1 is 34 and R2 is 7.3K, right? With these values, we shall go back to the actual analysis. Now, for going back to the analysis window, I'll make a changeover of the window, for which your screen may interfere for just 2-3 seconds. Just don't get disturbed. Just wait for 2 or 3 seconds. Okay? In the meantime, I shall make the changeover. So now I think you can see the new window. So here we have taken 34K and 7.3K. We discussed earlier, just now, that we shall analyze this performance analysis of this particular amplifier, how good or bad this amplifier. Now, there are few steps. Please follow my steps. First, let us see how the output looks like. This is the output oscillogram. Or I make it red and so this is the output. Here, the input is this blue line and output is this red line. And of course, the blue line and red line Y scale is different. I have made the scale such a way so that both are large enough to have a view. Now, this red line, have you noticed that On this end, or an upper end and lower end, they do not look similar. Whereas blue line, what your input was upper end and lower end was same. That means there is some distortion in the output. Some distortion in the output. So the upper end also you can see the upper peak is the it is 2 volt per division. Upper peak is around 3 volt, whereas lower peak is around minus 4 volt. So the output is not symmetric. So there is some distortion, right? And to measure how much is the distortion, I have connected a distortion meter here. See, the distortion shows it is 17.49, that means 17.5% distortion. This 17.5% distortion is really not good. Is really not good. You should not allow, even in your theoretical classes or in your college life, you should not allow more than 10%. And in your actual industrial life, you cannot allow more than even 1%. So what do we do? To make the decision, you first need to know why this distortion has come. Remember, I told you this base emitter junction of this transistor is a PN junction, which is a nonlinear characteristics. On a large signal, then what happens? You fall into the nonlinear zone. As a result, this nonlinearity happens. So you know the cause of this cause of this distortion. Then what is the remedy? You lower, you make the signal input low so that it is really a small signal amplifier, and within that low band, even if there is a nonlinearity, that should be acceptable. So what do we do, which is 50 millivolt peak now, 50 millivolt 02 peak, I make it low. Say I make it 40 millivolt peak to peak. And see what is the result. I make 40 millivolt peak to peak. Of course, as a result, when I made 40 millivolt, the output drops and the distortion becomes 13.392%. And even now, if you ask me, I'm not happy because the upper portion is flatter. The zero upper peak is around 2.6 volt or 2.7 volt. Lower peak is around more than 3 volt. So I make it still lower signal. This exercise you have to do in your laboratory, that, and you have to specify that your amplifier is good enough for what range of input. I make it still low. I make it say 30 millivolt. If I make it 30 millivolt, then see this, my distortion has come down to 10%. And you have to specify that your distortion is less than 10%, and with that 10% distortion, your teacher should accept your design. Now the red waveform looks more or less acceptable. So what is the maximum input to this design? 30 millivolt 02 peak, 30 millivolt peak. That means 60 millivolt peak to peak. So we write here maximum input X equal to 60 millivolt peak to peak. So this is the design you have met. The V in max is 60 millivolt peak to peak. And with that, what distortion you got? You got a distortion of 10%. Distortion is distortion is 10%, and if you tell it in dB, it is minus around 20 dB, because distortion normally we measure and talk in 20. So distortion is minus 20 dB, minus 20 dB. So your distortion is, okay, let me write it here. It looks better. Distortion is minus 20 dB, right? So these two we have measured. We have measured the maximum input for to this amplifier and distortion minus 20 dB. Then let us measure the gain. Measuring the gain is simple. Measure the AC input and AC output. The AC input is 30 millivolt peak to peak, 30 millivolt is 0 to peak, and AC output, yes, if to measure AC output, you just, what do? You just put a multimeter or a, this is creating some problem here, right? Just put a probe, voltage probe here at the output. Right? If you put a voltage probe here at the output, shows, I think you will find it difficult to see. I shall zoom in. Output shows voltage peak to peak at 4.54 volt. Output voltage 4.54 volt. Right? So V output is 4.54 volt peak to peak, and input is, I write, equal to 4.53 volt peak to peak, 4.53 volt peak to peak, and V input is 60 millivolt peak to peak. Input is equal to 60 millivolt peak to peak. Right? If that is so, 4.53 volt peak to peak and input is 60 millivolt peak to peak. Then what is the gain? Voltage gain AV is 4.53 volt by 60 millivolt. That means you calculate this, it is 4.530 divided by 60. The gain is 75.5. So gain is 75.5. This is the voltage gain, AV, right? Now, we don't measure current gain here because this is not a current amplifier. Measuring current gain in a voltage amplifier is meaningless. So then we measured so this probe now we remove. We don't need this probe anymore. We measured what is the input impedance and what is the output impedance. Output impedance is 10 kilo ohm because we have deliberately connected a 10 kilo ohm. So output raised impedance I have written 10 kilo ohm. What is the input impedance? Input impedance, what is the input current from here? So let me use a current probe. Let me use a current probe and then zoom in for you. Peak-to-peak current of 29 microampere. 29 microampere, right? So peak-to-peak current is 29 microampere, and this is peak-to-peak. And peak-to-peak voltage input is 60. So 60 milli divided by 29 micro will be approximately 2K, 2000. So it is 29 micro current, and voltage is equal to 60, voltage is 60 volt peak to peak, 60 millivolt peak to peak, 60 millivolt peak to peak divided by current is 29 micro. So input impedance is about 2068 ohm. I have calculated. So it is approximately 2 kilo ohm. So input impedance is approximately 2 kilo, right? 2 kilo. So we have measured the maximum possible input signal. We have measured the maximum output peak to peak. We have measured, of course, if your teacher wants it to be expressed in RMS, put the RMS values, but the ratio or gain will be same. And in input impedance is 2K, 2000 ohm, output impedance is 10,000 ohm. Now comes the frequency, now comes the frequency spectrum. Now, this is a amplifier that we have designed. Purposefully, we targeted to make an audio amplifier. And as I said repeatedly, audio signal is always tested at 1 kilohertz. But actual signal, when somebody speaks, normally the lowest frequency is around 200 or 256 hertz, and highest frequency around maximum around 3 kilohertz. But for the sake of theoretical calculation, the lowest frequency you can take 100 hertz so that your amplifier is always good. Now, for that, we need to take the frequency characteristics, for which there is a commercial name board plot, right? This is a board plotter. Sorry, this is a distortion analyzer. This is the board plotter. This is the frequency characteristics. Normally, frequency characteristics is expressed in dB, decibel. Now see, this is the flat zone of the characteristics. That means if I start from here, which is around 87 hertz, to around, this is 21 megahertz, your amplifier works as a flat gain. That means gain is throughout. If the gain would have been wavy, then you would need an equalizer after this amplifier. It says that for the entire audio range, this amplifier gain is flat. The result of this design is very good. Entire audio range, it is flat gain. Now, the lower cutoff frequency, I think you have already learned it in your network classes, and upper cutoff frequency is the minus 3 dB frequencies. Is minus 3 dB means, in linear terms, it means 1 by root 2 times. So here the dB, I hope you can see this. Yeah, here I can reverse it, right? dB rating is, here the dB is 37.945. Let's say 38 dB gain. So I go to a lower frequency where the gain is 38 minus 3, that is 35. 35. Then I use this cursor. Look at this. I'll make it around 35. I'll around 30, 35, 34.998 dB. So this is the minus 3 dB frequency. And what is this? 14.85865 hertz. That is around 15 hertz. So F1 is 15 hertz. You have a very good amplifier where the Your lower cutoff frequency is only 15 hertz. There is no human voice which can go to 15 hertz. And upper cutoff frequencies, again, we go to 35, 35, 35.7, 35.34.7, and 35.1. It is 81.6 megahertz, say 82 megahertz. So upper cutoff frequency is 82 megahertz. So frequency band is excellent. Frequency band is excellent. Now, before finishing this lesson, I want to give you a clue for your practical life. You will find this upper cutoff frequency is normally influenced by this output coupling capacitor. And lower cutoff frequency is influenced by this bypass capacitor. Lower cutoff frequency means the problem in low frequency. If your choice of emitter bypass capacitor is not proper, then the output of this amplifier at low frequency, that means at a bus voice, will be very distorted. I want to show you that also. Let me make this is 100 millifarad. Let me reduce this to 10. Let me reduce this to 10. Here it is 100. Let me make it 1 microfarad. Replace by 1 microfarad. This one is superimposing with the other 1 micro. Let me make it 1 microfarad. Right? See, lower end has got distorted. Upper end is still good. Lower frequency response has got distorted. Let me make it 10 microfarad. Make it 10 microfarad. See, it is little better. Still not very good. Let me make it 100 microfarad. Now it is good. Right? So you will remember for your practical life that emitter bypass capacitor affects the lower cutoff frequency or low frequency response. And high frequency response is affected by these coupling capacitors. So this analysis of this amplifier we have done, and what we have found really, I removed this probe also, it makes it look clumsy, that maximum input that you can give is 60 millivolt peak to peak, and our output voltage at that time is 4.53 volt peak to peak, and input is 60 millivolt peak to peak, and gain is 5.5. Input of this amplifier is 2K, output impedance is 10K. And lower cutoff frequency is 15 hertz, upper cutoff frequency is 82 megahertz. And with this, our distortion is minus 20 dB, right? That is where I want to finish your lessons on BJT common emitter amplifier. In our next lesson, we shall take, because this BJT amplifier, I think it is the longest part of your syllabus, because you have to start from device, understanding how the BJT works, and finally you will end up in all through biasing, bias stability, this and that, many calculations. You finally know how to design a BJT amplifier. And my purpose was to show you right in front of you, your eyes, how to design a BJT amplifier and how to test that amplifier also. So we end this chapter here. Thank you very much for your cooperation and your patient listening. In our next lesson, we shall go to the next topic of your syllabus.